Other than the brain, I'd say your intestinal tract, your digestive system, is one of the smartest organs in the body. Why is that? Well, the digestive tract has its own nervous system. It's got its own brain. In fact, we call it the enteric nervous system. The enteric nervous system, because the GI tract is able to act on its own without having to send neuronal information or signals to the brain or the spinal cord to regulate its action. For example, if we're in the presence of a really awesome meal, something that's good enough for any hero in a half shell, and we consume this meal and it goes through our mouth, the esophagus, and it lands in our stomach right here, and we've got our food right there. What we initiate from this, thanks to our enteric nervous system, is called the gastrocolic reflex. The gastrocolic reflex. That involves the stomach, the gastro part of this reflex, as well as the colon. Because what happens is that the presence of food in your stomach, as signal 1, tells the colon here it's time to make way for food that's coming down. So your colon will actually, as a response, take food that's in here and push it further south. And it does so to make room for the food that we're eating. That's the reason why after you eat, you feel like going to the bathroom. It's not because the food you just ingested is about to come out. It's because food that you ate a while back has come to the end of its journey, thanks to the gastrocolic reflex. So neuronal control is one mechanism our GI tract uses to control what we do when food is present. The other component we'll focus on down here is hormonal control. Now, hormones, as you might recall, are substances that are released by tissues in our body that then go through blood vessels, like this guy right here, to go to some target organ or target tissue to cause an effect. So I'm going to talk about a couple of hormones here that regulate our GI tract when food is present. So the first hormone we're going to talk about is called gastrin. Now, gastrin is a hormone that's released when we notice that there's food in our stomach. Gastrin is released out of the stomach to go to our bloodstream and then come back out actually to the stomach to stimulate the secretion of digestive juices. So recall that when we have food in our stomach is going to cause gastrin to be released from mucosal cells. The gastrin will then go on to cause secretion of a couple of things. One, you're going to get stomach acid or hydrochloric acid to be released from parietal cells in the stomach. You're going to get pepsinogen to be released from chief cells in the stomach. And remember, this is the inactive form of pepsin that must be cleaved to become active to digest protein. The other thing that gastrin does is that it increases stomach motility. Remember that one of the functions of the stomach is to churn food that's present. It's not just to release acid and pepsinogen that's going to digest food. It also physically breaks down the food. So we result in something that's called chyme. And I'll write that right there. Chyme is what the stomach sends to the duodenum. Now, gastrin release into our bloodstream is not unopposed. It's checked when the stomach acid reaches a pH of 3. When this occurs, then we're going to have a decrease in gastrin release. So low pH decreases our gastrin release. So I'm going to say red is inhibition, green is the go-ahead or the green light. So remember, the next part of our digestive process involves delivering chyme to our small intestine, and we'll specify the first part of our small intestine, and remember that's called the duodenum. So chyme that's delivered to our duodenum. Now this is going to cause the release of two other hormones. The first hormone I'm going to talk about is called secretin. So secretin. And I've sort of started the color scheme here. But once we have chyme delivered to our duodenum, secretin is released into the bloodstream. And it goes two places. So first it's going to go down to the pancreas. that I could have drawn up here on your GI tract. It sits about right there in the duodenum, but I'm just going to write it out over here. So secretin in the pancreas is going to cause the release of bicarbonate-rich solution. So this bicarbonate-rich solution is going to involve our pancreatic enzymes, but the most important part that we want to focus on here is the bicarbonate. And why is that? Well, the whole stimulus for secretin release was the acidic chyme that was delivered to our duodenum. So of course we'd want to release a base like bicarbonate to neutralize that acid. The other place secretin is going to go from our bloodstream is actually right back up into the stomach. This is going to cause an inhibition of stomach motility and acid release and pepsinogen release, the kind of things we saw happen with gastrin. The other hormone that's going to be released because we have chyme in our duodenum, the acidic chyme in our duodenum, is called cholecystokinin. And as you remember, this is a hormone that's related to our gallbladder. And just like secretin, our cholecystokinin is released from our intestinal mucosa, so I can draw it coming from, say, here, into our bloodstream, and it's going to go two places as well. One, it's going to go to the pancreas to stimulate the release of our pancreatic enzymes. So release our pancreatic, I'll just write panc here, pancreatic enzymes. And this will help in our digestive process. One of the enzymes that is released from the pancreas that I'll explain in a minute, it'll help clarify things, is lipase. Remember, lipase is used to break down lipids, right? So that's what the LIP stands for. We're breaking down lipids. The other thing cholecystokinin is going to do is go through the bloodstream and arrive at our gallbladder. It's going to go to our gallbladder. And at our gallbladder, cholecystokinin is going to cause the gallbladder to contract. So contract our gallbladder. And what do you think happens when the gallbladder contracts? What's the main function of our gallbladder? Well, if you remember, the gallbladder is holding bile that was produced in the liver. So when you squeeze the gallbladder, you're going to pump bile out of the gallbladder into the cystic duct and down and out through the common bile duct into the duodenum. And that's going to help emulsify fat. And lastly, the other thing that cholecystokinin does is that it comes back here and decreases our stomach motility. We want to slow down the release of our chyme from the stomach because we need some time to process what we already have in here. Now, is it plain old chyme that causes our cholecystokinin and our secretin to be released into the bloodstream? Or is it something more specific in the chyme? Well, let me ask you, why do you think cholecystokinin was released? If we had to point to a specific nutrient that was in the chyme that requires then our gallbladder to contract and release bile and have our pancreas release an enzyme like lipase, what kind of nutrient do you think I'm suggesting here? Or macromolecule? Well, if you said fat, you're absolutely right. It's the fat in our chyme that specifically causes cholecystokinin to be released. Okay, so what about our secretin? Well, again, this is up to you. Think about what's happening because of the secretin. The main thing here is that we're having bicarbonate be released. And so bicarbonate's a base, and we talked about how that's important for neutralizing our acidic chyme. So it's not really a macromolecule that causes secretin to be released. It's hydrochloric acid. It's the acidity of our stomach acid that's now delivered to our duodenum that causes the need for our bicarbonate-rich solution from the pancreas. So great. I think we have a good idea of how our GI hormones are helping us so far, at least in our intestinal tract. Now I know that I gave a little shout out to the pancreas here, and we separately talked about how insulin is released when we have an increase in glucose levels in our bloodstream to help us store that glucose for later use. And then the opposite occurs when we have a decrease or low levels of glucose and we cause glucagon to be released to increase the amount of glucose then in our blood. Together, these hormones work in a very beautiful manner to make sure that we have the correct hormone to respond to the right stimulus so we can get food that just arrived in our stomach processed all the way to the very end, thanks to our hormones. And as we mentioned earlier as well, thanks to our enteric nervous system.